We move now into the Mesozoic era, and of its three periods, the Triassic is the oldest. Pangaea is still the dominant landmass on Earth, although by the end of the Triassic we'll see signs of its eventual demise. Much of the climate was arid or semi-arid, floodplains, deserts, typical arid region environments. The rocks here along the Colorado River at Lee's Ferry in northern Arizona are a series of river channel and floodplain deposits of the Triassic. If you recall, the end of the Permian saw the largest mass extinction of the Phanerozoic eon, where over 90% of all species were wiped out. So this is a time of survivors, and some of the survivors included the reptiles, of which older versions like Postosuchus here, but there are also newcomers, the dinosaurs, Coelophysis here, competing with Postosuchus for the meager resources available at the time. Mammals would also make their appearance, but would have to lay low while the reptiles had their day. The Triassic period stretched from 252 to 201 on the ICS time scale, the first period of the Mesozoic era, split into lower, middle, and upper parts. And it's named for a region in Germany that has three rock sequences of this age. These are Triassic rocks in the Bavarian Alps. This is the Watzmann Massif, layered Triassic limestones. Geography of the Triassic, of course, is dominated by Pangaea, pole-to-pole landmass. Along the equator was probably tropical or subtropical, but to the south in the Gondwana region, huge areas of desert regions, arid regions, coastal plains, possibly forests in the South Pole region. The same would go for the northern part of Pangaea, we know as Laurasia. Stretching from the equator, we get into more arid regions, deserts and coastal plains, and more forested regions toward the poles. Off to the west remains the great superocean Panthalassa, and on the western margin of Pangaea is this subduction zone, which will persist through the rest of geologic time. So here it's an ocean-continent convergent boundary, and as it stretches to the north it becomes more of an ocean-ocean convergent boundary. The subduction zone actually wraps around into the eastern hemisphere, and you can see that Pangaea is almost entirely surrounded by convergent margins. In the eastern hemisphere, we have this broad ocean basin, which is within the jaws of Pangaea. So the upper jaws here surrounding the Paleotethys Ocean, the larger of the two oceans, and then the lower jaws, that is Tethys itself. So the Tethys is known as the Proto-Mediterranean, and the Mediterranean Sea today is actually the only remaining vestige of this ancient ocean. Well, let's look at Ron Blakey's global reconstructions. This is for the middle part of the Triassic, around 240 million. Here's what we would call the Western Hemisphere, showing Laurasia and Gondwana. There is the Great Alleghanian Highlands, weathering down the east-west mountain range there, forming the boundary between Laurasia and Gondwana. The island arc off to the west side of Laurasia with its foreland basin created as it loads up onto the margin of Laurasia. Off in the eastern hemisphere, the jaws of Pangaea. And they are slowly, relentlessly closing because of the subduction zones present in this area, and the Paleotethys and Tethys oceans will be consumed as a result of that. As we move into the late Triassic, about 220, you can see, again, we still have Laurasia, broad areas of desert region, as is the case in Gondwana. But in between, you can see some changes here along the Alleghanian Highlands. And this is the beginning of the end for Pangaea. The rifting progresses along an axis like this, which is not quite parallel to the Alleghanian Highlands. Okay, so part of the The rift is like this, and part of these mountains will be kept on the Gondwana side, and the other part will be on the Laurasian side. So this rifting is initiating during the Triassic. Again, during the late Triassic, we have the Tethys widening and the Paleotethys shrinking. So if we do the flip chart back to the middle Triassic, we can see the situation between Laurasia and Gondwana and the beginning of rifting into the late Triassic. In the eastern hemisphere, we can see some of the changes going on with the Tethys oceans from middle Triassic to late. So basically the expansion of the Tethys ocean during the Triassic. Looking more closely at Laurasia, again using Ron Blakey's work, you can see the equator for reference. So Laurasia north of the equator and Gondwana to the south. Here are the remnants of the Alleghanian highlands. And you can see the rifting starting to occur even in the early Triassic, with fingers of the ocean extending inward into Pangaea. So we'll see that develop over time. On the west coast, we have the subduction zone with its tectonic chaos, with island arcs and terrains being accreted. Huge areas of continental plain, mostly arid regions, large continental shelves. If we move into the middle Triassic, it's a similar situation. Rifting has progressed, and so we're getting rift basins developing. Still, we don't have a consistent seaway developed yet, but that's coming. And broad arid and semi-arid regions, coastal plains and broad continental shelves to the north, and then an active margin off to the west. And then the late Triassic. Again, just a slow, progressive continuation of rifting. So Pangaea is starting to rift apart, but it's still Pangaea. You can still walk from Gondwana to Laurasia and points north. For the most part, it remains a large landmass with huge plains, an active western margin, and continental shelf to the north. And this is at about 210 towards the end of the Triassic. Let's back it up to the early Triassic, middle, late. Watch the progression of the rifting, early Triassic, middle, late. Early Triassic, we're having, again, orogeny going on in the western margins. And look for new terrains to be coming across the Panthalassa Ocean, which are going to be important in the future on the western coast of what will be North America. And there they are, like tectonic waves crashing on the shorelines of Pangaea and what will become North America. Focusing in on western Laurasia, the entire margin now is becoming active, whereas it was just the northern part that was affected by the earlier antler orogeny and then the Sonoman orogeny, and the southern part was more or less unaffected. Now the whole margin is becoming active. It's a region of compressional tectonics with fold and thrust belts, fold mountain ranges and thrust faults. We think that much of the area of Nevada was the mountains formed from this collision. The Golconda thrust is the leading edge of this tectonic activity. And in front of this developing tectonic area, a foreland basin will develop into the Triassic in this area. And so this basin is again a response to the addition of tectonic material added on to the west margin of Laurasia. And this is a broad, shallow marine foreland basin. related to the Sonoman Highlands. We will see some activity down here. Gone is the shallow, passive continental margin off the west side of Arizona. Now it's become active. Well, there's so much land area that there's a lot of continental sedimentation. And most of this is fluvial or stream related. River channels, floodplains, river deltas. Here's a picture of what the late Triassic might have looked like. Broad areas of fluvial plains, some mountains developing near the edge of the continent, and then the island arcs off to the west. This is a depiction of what the area might have looked like, with the tectonic highlands off to the west and streams draining off those highlands, depositing sediments in broad braided stream environments and river floodplains. Some of the creatures at the time during the Triassic would be small dinosaurs and some early crocodile forms. Tectonics during the Triassic includes significant rifting of Pangaea, and this will ultimately form the Atlantic Ocean Basin and the Gulf of Mexico. So if we look at the Earth here, we can see Pangaea with Alleghanian Highlands for reference, and the rifting will begin along either side, and then there's the Eastern Hemisphere. So the tectonic map of the later part of the Triassic and shows in red lines rift zones and mid-ocean ridges. You can see the rift zone progressively encroaching into Pangaea on the east side here. There's a subduction zone on the west side, an active collisional orogeny going on here. That's the Sonoman orogeny that's still ongoing through the Triassic. But significant tectonic activity would be rift related, and this shows the typical sequence of the rifting of a continental plate. Heat is driving this, uplifting the continental plate, stretching it, causing decompression, melting, eruption of basalts, sometimes flood basalts, huge volumes of basalt in this rift area. As the plates start to separate, you get tensional stresses causing normal faults and rift valleys developing, and those are filling with volcanic material. And over time, as this progresses, the plates get farther apart. Now you have two separate plates where you used to have one. And these plates are separated by a new ocean basin in between. This ocean basin is being made by the melting of the mantle, producing these basalts progressively more and more over time. And so that's how ocean basins are formed. So at first it's a narrow seaway, and with time it becomes a much broader ocean basin. This is the scene in eastern Pangaea right now, where we're just getting these top two kind of sequences. We haven't progressed this far yet. That's coming. As I mentioned, rifting would begin on the eastern side of Pangaea and more or less unzip to the west and southwest. So progressively more and more rifting, and eventually these rift basins would evolve into a narrow ocean basin, a seaway, and then finally the more robust ocean basin we know as the Atlantic. But for right now in the Triassic, we are in this early phase right here. Let's look at the tectonics of eastern Laurasia, the rift basins that are forming there. So this crustal extension spreading is creating rift basins in the eastern part of Pangaea, and these are still exposed today on the east coast of the U.S. Here's a map of where they are located, both at the surface in blue and in the subsurface in red. We know of the subsurface locations from geophysics and well log data, various basins from Connecticut down through New Jersey and Pennsylvania. The Gettysburg battlefield is actually a rift basin down through Virginia into North Carolina. In fact, there's actually a lot of Civil War history related to these. If we look at a tectonic cross section, we can see the incipient rift developing So this is what's going to become an ocean basin here. And on either side, the North American plate and then the African plate. So this is all Pangea right now. It's still one plate. It hasn't totally rifted apart yet. And on either side, because of the tensional stress, we have faults that are normal faults. Okay, so the hanging wall here is slipping down relative to the footwall, and it's a bunch of normal faults on either side of the rift axis. So these rift basins themselves are typically asymmetrical, meaning that there's a major fault only on one side of the basin. And so what this does in effect is drop the basin down like a trapdoor. So it's hinged on the one side and it drops down along the normal fault. And we call this kind of rift basin a half-graben. The axial rift right here is what we call a graben. That's German for ditch. A rift basin where you have a normal fault on either side of the basin. So it's a fault-bound basin, faults on either side. A half-graben is simply where you have a basin with only one fault. During this time, the Gulf of Mexico actually starts to form. Tectonics of western Laurasia include the Sonoma orogeny. So this began in the Permian at about 270 and is progressing into the Triassic until about 245. And if you remember, it involved a collision of a small microcontinental fragment called Sonomia and some associated island arc terrains, and their collision with the western margin of Laurasia. So this little diagram here shows a simple progression. There's a west dipping subduction zone, which was bringing these fragments closer and closer to Laurasia over time until they finally came into contact, were loaded up onto the margin, weighed down the margin, created a foreland basin. That is the Sonoma orogeny. This picture here shows the terrains added, not just by the Sonoma orogeny. Here's Sonoma here, so a portion of the western U.S. got its origin with this orogeny, but also the previous antler orogeny, much smaller amount of material. And then these successive collisional orogenies would bring in more terrains added to the west coast over the Mesozoic, from California through Oregon and Washington, through Canada up into Alaska. So a whole suite of different exotic or suspect terrains, as they're called, accretionary terrains. One last thing to note here is that this subduction zone for the antler orogeny and the Sonoma orogeny was west dipping, meaning that it's being subducted down off to the west. Material is coming closer and closer from the west there. Well, after the Sonoma orogeny, after it collides, this material collides, it shuts off the subduction zone, but there's still compression, and there is a oceanic plate behind Sonoma there, which still is moving to the right, to the east, and over time it's going to create a east dipping subduction zone. And so this diagram shows that evolution from the beginning of the Sonoma orogeny, as you see this west dipping subduction zone here, the Sonoma island arc and continental fragment coming closer and closer, and then colliding with Laurasia, creating a foreland basin, lots of sedimentation, Sonoma highlands, all that. But the main tectonic change here is this new subduction zone, which is east dipping. So it was formerly west dipping during the previous antler orogeny and the Sonoma, but then on the backside of the Sonoma collision zone there, that oceanic crust started to subduct down to the east and would continue forming an east dipping subduction zone. This is a big deal because this changes the nature of tectonics on the west coast of Laurasia and what will become of Laurasia, North America, for the rest of geologic history. Rocks of the Triassic and central Pangea include the Central Atlantic Magmatic Province, or CAMP. And this is a flood basalt area that erupted in the late Triassic around 200 million years ago, so right at the very end of the Triassic. Massive flood basalt eruption of 2 to 3 million cubic kilometers. So this is 4 to 6 times the Deccan Traps volume. It's a massive eruption of mafic volcanics. This shows Pangaea at the time and the extent of the magmatic province, covering a bunch of different continents. And so we think this was related to the rifting and eventual breakup of the supercontinent. Flood basalts are typically one of the steps that occur in the evolution of a supercontinent breakup. Stretching of the lithosphere, melting of the mantle, and huge outpourings of basalt at the beginning. These outcrops are found on different continents now that were formerly connected, but now they're separated by the Atlantic Ocean. This is the Palisades Sill along the west side of the Hudson River in North America. And then this picture here is from Northwest Africa. That's a diabase sill, and then these are mafic flows and related intrusives of the Central Atlantic Magmatic Province, or camp. So in eastern Laurasia, rift basins are a major depositional environment, and in these basins are both marine and non-marine sediments that are being deposited. So as the basins form, erosion of the highlands and clastic material, conglomerate, breccia, sands, and muds being shed off those highlands into the lower basins, filling them up over time. Ponding in the basins, giving lakes which might dry up and give evaporite deposits. So various kinds of non-marine sedimentation, fluvial sedimentation, stream related. But also if the basins themselves get low enough, the sea will come in and at first get shallow water environments that are subject to a high degree of evaporation, a lot of evaporite salts, and this will give you playas and salt pans and things like that. So both marine and non-marine sedimentation, mostly clastic and evaporite sediments deposited in these basins. This picture shows some of these basins forming in the interior of Pangaea and what will become North America and Africa. Some of the more marine settings are a little bit farther east. Also in these rift basins is a major package of rocks called the Newark supergroup and related diabase. This material is late Triassic into the early Jurassic in age, and it's a thick accumulation of mostly non-marine rift basin sediment. At least 6,000 meters of this material, which originally was deposited in alluvial fans at the flanks of the rift basins. That fan material would be sedimentary breccia and conglomerate, and away from the mountains, closer to the interior of the basin, the class size would decrease and you get more sands and muds. So this shows the type of sediment being deposited. Here is the half graben with the main bounding fault on the west side. So the highlands over here are eroding, and in red these are fanglomerates, which are breccias and conglomerates, and farther and farther the sediment that's finer grained, and that's sandstone, and then mudstone in gray. So a typical decrease in grain size with distance from the source. Other environments would be lakes. Ponding in these basins would give you lake sediments. Playas, as the lakes dry up, give you various evaporites. Red beds represent this kind of environment. Also, with rifting comes volcanism and basaltic lavas, mafic intrusions called diabase. So a whole suite of mafic lava flows, sills, and dikes that are related to the Newark supergroup. Here's a cross-section of supergroup sediment with a thick mafic intrusive there, and this is the Palisades Sill. So an intrusion along the layers, that's a sill. And this is the Palisades of the Hudson River. There's the Hudson. And here's what it looks like for real. There's the Hudson River looking north along the west side. So this wall here is actually a Triassic and early Jurassic sill. This feature right here actually extends from New York City north along the Hudson up towards West Point. Also in eastern Laurasia, in these rift basins, are major evaporite deposits. In these rift basins that are progressively becoming larger and larger would be incursions of the ocean, a lot of evaporation, creating an environment for the formation of evaporite. So a thick sequence of evaporites in these basins extends along the east coast of North America today, and we can see them now on the subsurface. So originally these would form as the rifting progressed, eventually opening up the whole Atlantic Ocean basin between the various parts of Pangaea. These salt layers were laid down and then covered by younger sediments. Okay, so huge, vast salt plains, much like here in Death Valley, with salt polygons encrusting the surface here. If we look from the Gulf Coast across the Gulf of Mexico to the Yucatan Peninsula, we see these evaporites in the subsurface. So there are Triassic and Jurassic salt layers present in the subsurface that we can see with drilling and with seismic studies. We've mapped out these layers. One major one's called the Lujan salt, and salt is relatively ductile at surface pressures, and so it can flow. And as it's progressively buried, it's under more and more pressure from compaction, and the salt starts to move. It'll collect in certain areas, and it's buoyant, more buoyant than the surroundings, so it'll start to rise, much like the blob in a lava lamp. And it might continue to rise as long as it can, and it starts deforming the rock around it, and actually can form these salt pillars called salt domes. And they're very important economically because related to these salt dome activity are petroleum deposits which collect around the salt dome. So the oil industry is very interested in these kind of structures because these provide different kinds of traps for the hydrocarbons. And quite commonly there are significant oil and natural gas reservoirs there, all due to evaporation of seawater in these rift basins back in the Mesozoic. Well, in western Laurasia, we have the Moenkopi Formation, and it's a Middle Triassic unit about 245 to 240 in age, and it's mostly a collection of fluvial sands and muds, so stream-related sandstone and mudstone, and there are minor amounts of other things like evaporite and limestone a little bit farther west. This is a strat column from Ron Blakey showing the Triassic and Jurassic in northern Arizona, and the Moenkopi is the oldest Mesozoic formation in northern Arizona, Triassic, and it's made up of a number of different members, okay, which come and go across the region. The Wapatki member here is what we see at Wapatki National Monument. In fact, the ruins themselves are built of the Wapatki member, Moenkopi. In the Holbrook area, there are more sands related to the Moenkopi, and that's the Holbrook member. As we go farther west, there are other types of member like the virgin limestone and the Schnabkaib member, which is more gypsiferous, more gypsum in it. You can see the difference between western Moenkopi here with the different colored layers, meaning different compositions, versus the Moenkopi here, which is more monolithologic. It's almost all mudstone and maybe some siltstone in there. So this is Lee's Ferry area, a little farther east, and this is over near Zion National Park to the west. Another classic rock formation in the southwest is the Chinle Formation. And it's a little bit younger than the Moenkopi, late Triassic, so 227 down to about 209 in age. Again, mostly continental stream deposit, fluvial sands and muds, sandstone and mudstone with a smattering of volcanic ash thrown in for good measure. Here is the Chinle sitting right above the Moenkopi. And again, like the Moenkopi, there's a number of different members in it. It's not made of all one composition, so we break out these different members. The base is a conglomerate called the Shinarump, very distinctive name, and it's a very distinctive unit. It actually forms cliffs, very resistant kind of unit. And above that is the petrified forest member, and this is present farther east in Holbrook and in the Painted Desert area, and it includes an abundance of petrified wood. Okay, and so Petrified Forest National Monument is in the Petrified Forest member and others. This is where we see the highest concentration of petrified trees. Okay, so these are fossilized conifer trees of various kinds, and they're created as there's a forest there, and there are volcanic eruptions off to the southwest. Volcanic ash, airfall ash, falls on the Holbrook area and buries this forest in ash, and as the trees die and fall over, they don't decay, they fall into the ash, and groundwater takes silica from the ash, volcanic ash, very silica rich, and replaces the organic material in the tree with the silica. So this is the petrification process, and then we get replacement of not only the trees, ferns, and other plant material as well. It's very common in parts of the Chinle. The Painted Desert here, very colorful, and the reason why it's colorful is because there's different types of mudstone, gray volcanic ash, different kind of soil layers in there, maybe some evaporite layers, some lake deposits, all making up the Chinle. So Painted Desert itself is due to the different environments and different types of sediment being deposited at this time during the Triassic. Petrified Forest National Park is also largely Chinle Formation. Well, the climate of the Triassic is all about heat. So it's really a continuation of the warm climate of the latter part of the Permian, after the massive Siberian trap flood basalt eruption really altered the climate. We've progressed into what's called a hothouse kind of Earth. And so that is the end of the Permian, and this would continue into the Triassic for some time. So most of the Triassic is in this area here, relatively warm. So it's very gradually decreasing with time away from this latest Permian hothouse. So it's pretty much warm pole to pole, not a whole lot of significant ice present. Large areas of arid and semi-arid climate. This could possibly be the warmest the Earth has ever been, this stretch between the end of the Permian through the Triassic. So again, present day temperatures are right down here. So it's much, much warmer than today. You might ask how we know what the climate back 200 million, 240 million years ago when nobody was around. Well, we use the various rock types that represent deposition in various climates. We can also use fossil plant data to help reconstruct what the environments would have been. Tropical plants versus more temperate plants, that kind of thing. So this is a picture of various rock units deposited in the lower or early Triassic versus the upper or later Triassic. And it just represents the distribution of various rock types which allow us to reconstruct the climate. And these rock types would include coal, which would be more of a subtropical kind of plant environment. Evaporites, more of a high evaporation, arid or semi-arid environment. Tillite is a glacial deposit, which would represent more of an Arctic environment. Well, life of the Triassic, like I said, it was a time of survivors. And most of the survivors would recover fairly slowly from this massive Permo-Triassic extinction. If we look at it, here it is, third in the sequence of the big 5 mass extinctions, and it's the big one, the end of the Permian. So here we are at the beginning of the Triassic, from levels of life that haven't been seen since the earliest part of the Paleozoic, back in the earliest Ordovician. So there's a slow but sure rebound into the middle part of the Triassic as life builds back again to higher levels. And what we see in the rock record is that the synapsids really took a hit from that mass extinction, and very few of them continued on into the Triassic, as opposed to diapsid, the true reptiles, which were much more abundant. So they seem to fare better through this mass extinction. So the mammal-like reptiles are the synapsids. They're the ones that had trouble and struggled, versus the true reptiles like we're going to see, the dinosaurs would at least not struggle as much. Before we talk about dinosaurs, let's talk about marine vertebrates, specifically marine reptiles. And so to set the stage for this, we had the giants Permo-Triassic mass extinction about 252. And what we see in the rock record is the very rapid evolution of reptiles of a marine origin. And so we think they evolved adaptations for the marine environment. So whether they were already somewhat aquatic or semi-aquatic, we see fully aquatic reptile forms now into the Triassic very early. And this includes ichthyosaurs, a very common type of marine reptile, and they're first seen around 250. So again, that's only a few million years after the mass extinction, which occurred at about 252. So these are very abundant marine reptiles, very streamlined forms here. They almost look like dolphins, but they're not. They're reptiles. Dolphin's a mammal. This is Chaosaurus here, an early ichthyosaur, and they would evolve much larger forms, like a couple here. Here's a person for scale. This is Shonisaurus, and then Shastasaurus, this guy here, maybe up to 70 feet in length. So giant ichthyosaur forms, and we'll see those continue through the Mesozoic. Nothosaurs are a slightly different type of marine reptile. They're a little smaller, but they have a longer neck, smaller head. They have teeth here. Okay, so they're reptiles. They have arms, not paddle-like limbs or anything like that, like the ichthyosaurs. They have arms and hands that don't have fingers, but they're webbed, so more suited to aquatic environment. Long tail here. These we think are ancestors to later marine reptiles called plesiosaurs. We'll see those later in the Mesozoic. And a few other types of marine reptiles include placodonts and turtles. Let's talk about Triassic land animals now, and archosaurs. The archosaurs are a group of animals, mostly reptiles, that include crocodiles, dinosaurs, birds, things like that, and their ancestors. And so early archosaurs were present in the Triassic, and these again were fairly mobile ancestors to what would become dinosaurs, pterosaurs, and even crocodiles. Where we are on the chart here, if you remember, there are different types of reptiles. The mammal-like reptiles would evolve in this direction. The true reptiles, the diapsids, would go here, and then the archosaurs more or less are what are coming before all these other groups. And another word for these is thecodonts. So these aren't dinosaurs, although they can have some characteristics of them. They would evolve into later forms of dinosaurs, birds, crocodiles, things like that. So these were the dominant Triassic land vertebrate. Here's Tycinosuchus at the shoreline with some nothosaurs in the water there. And this is Postosuchus. It looks like kind of an upright crocodile. Walked on 4 legs, could even walk on 2 legs, with a dinosaur kind of head on it. So kind of a hybrid body form there. But these are ancestors to dinosaurs. The word suchus here refers to extinct crocodile-like animals. So when you see suchus, it's usually referring to somebody like that. Let's take a look at the phylogeny of these archosaurs. So here's the group Archosauria, and this is according to Nesbitt 2011. There are actually different classifications done at different times. So this is a more recent one, and it shows the groups getting smaller and smaller. All of these are extinct except for a few, and so the archosaurs would evolve into smaller groups, including the dinosaurs, which have different kinds. There's dinosaurs here, pterosaur, the thecodonts here. So these are part of the Suchia. These are all extinct, the little crosses here. All those are gone. What still survives of this group is the crocodiles. So these are archosaurs that are still alive today. And the birds. So basically the birds have lasted. Basically archosaurs evolved this way into dinosaurs and eventually into birds. So birds and crocodiles are two of the still existing forms of archosaurs. Back in the day, though, these were the dominant land animal, and they would become hugely successful throughout the Mesozoic. Okay, and this is just a cool looking comparison of the sizes. So the largest sauropods here of the various types of archosaurs, from the giant crocodile forms through tyrannosaurs into the huge sauropods. These are all archosaurs, whether it's a dinosaur, pterosaur, or bird. The time has come to talk about dinosaurs. So the first appear by about 233 million, and these first dinosaurs were relatively small compared to later forms. And there's a couple different kinds. Herrerasaurus is one of the first, basically, that we would find, and it was fairly large compared to a human, maybe up to shoulder height or so. So those would range in size. Coelophysis here is a little bit smaller. Again, bipedal on two legs, relatively sleek. You can see the body form there, nice and slender. Here's a very well-preserved sample of Coelophysis. Note the death pose here with the neck craned back towards the tail. So as Coelophysis died here, it was buried quickly and its tendons constricted basically into that death pose. So we also have the very small Eoraptor. These look like the later velociraptors and other kinds of dromaeosaurs, but these are very early dinosaurs, okay, that had just evolved from the earlier archosaurs. All the other later versions, these are the first dinosaurs which would have to compete with those large archosaurs like Postosuchus. Good luck. So there were reptiles in the water, there were reptiles on land, and yes, reptiles took to the air. So air vertebrates like pterosaurs. So reptiles like this were first seen at the beginning of the Triassic by as early as 228. So soon after dinosaurs evolved, come pterosaurs. Is Priondactylus, the oldest known pterosaur, is an age of about 228. And so these were fairly lightweight. We think they had hollow bones, which would allow them to take flight more easily. Eudimorphodon here is a small pterosaur. That's about a meter or so. Not huge, but it's not tiny either. Here's the family lineage. So they're amniotes and they're diapsids, and of course they're archosaurs, but they are not dinosaurs, they're pterosaurs. You could say these are flying amniotes. You could say they're flying diapsids. You could say they're flying archosaurs. And they are also flying reptiles. Just don't call them flying dinosaurs. Well, some other land vertebrates included our first mammals. So mammaliforms, the late Triassic. These came after the first dinosaurs and pterosaurs. Fairly primitive mammalian forms, small, inconspicuous descendants of the therapsids. Remember the therapsids? Here's the family tree. We had pelycosaurs, the sailbacks. They would evolve and go extinct in the Permian. Then the therapsids, these are all mammal-like reptiles, and they would have fur and claws and an upright posture, evolve into cynodonts by the end of the Permian. They would make it through the mass extinction and evolve into these mammaliforms. So these are the precursors to class Mammalia. During the Triassic, they had a fairly rough time. They were competing with these other organisms like the archosaurs, which included things like Postosuchus and Coelophysis. Little Morganocodon, watsoni, doing battle with Postosuchus or Herrerasaurus, no match. So pretty much had to bide their time and be patient. Well, a lot of these organisms had to eat, and so the plant life of the Triassic was varied. There was quite a variety of different types of plants, including spore plants, that are decreasing in abundance. The spinopsids have been around for a while, since the Paleozoic. They are decreasing rather quickly in abundance. Remember the segmented plants. Spore ferns are still around. Lycopod trees are drastically dwindling, and they are giving way to the seed ferns, which are very abundant, and also the gymnosperms, which are really starting to take off in the Triassic, including the conifers and now the cycads. Cycads are a new plant coming on board here. And so these are seed plants that can tolerate these drier, warmer, extreme environments of the Triassic. Cycads, conifers, even ginkgo are abundant in the Triassic. Spore plants are declining. Still no grass and no flowering plants. That'll have to wait. So, still in the Triassic, but things are changing. Well, we end the Triassic with, you guessed it, a mass extinction. So this event occurred at the end of the Triassic, and on this chart here it shows the Paleozoic at 300 down to the Permo-Triassic boundary, 200 down to the present. Okay, and it shows the percent extinction. So this is a little bit different. The other graphs are showing the amount of actual organisms. This shows the percent extinction. So the higher the peak, the greater the extinction event in terms of the number of organisms gone extinct. Okay, and so you can see the Permo-Triassic one is the biggest one here. There's a number of peaks here, but the three biggest ones in this part of the timeline are the Permo-Triassic, that's one of the big five, the end of Triassic, that's another one, and then the end of the Cretaceous. So this extinction here took care of about 30 to 40% of all marine genera. So this is one way we look at extinctions. We're looking at marine organisms, and we're not looking at species here. The genus level is the next higher level. And so sometimes we see mass extinctions classified by the number of genera involved or the number of species. In this case, it's genera, which is plural for genus. You can see that the end of Permian one was the highest one, followed by the end Triassic, which was fairly high as well. Notice that it is at least as high as the end of Cretaceous mass extinction, which is the one that took out the dinosaurs. This gets all the attention. No one's ever heard of the end Triassic mass extinction, and it was just as significant as the one that occurred at the end of the Mesozoic. So almost half of all land tetrapods would be wiped out by this one. So marine reptiles were significantly affected. Maybe a third of them go extinct. Almost half of your land tetrapods, which included therapsids and other kinds of archosaurs. When we look at the diapsids that were affected by the extinction, here's the Triassic and here's the Jurassic and here's the boundary, the extinction event. And so marine reptiles really took a hit. Snakes would continue through, crocodiles would continue through. So some of these archosaurs would continue, but some of the early archosaurs were hammered and they did not make it, including a lot of these forms like Postosuchus. These thecodonts or early archosaurs here were the vertebrates that didn't make it. And of course the dinosaurs did, pterosaurs did. So they inherited the earth absent of all these other predators. And so this mass extinction really paved the way for dinosaur rule for the rest of the Mesozoic. We think it was due to a massive flood basalt eruption. And again, when you look at the age of the central Atlantic magmatic province, it is 201, so it is right there at the end. So there's a nice correlation between flood basalt and mass extinction. We see this in the Siberian traps. We think that's a likely cause for that mass extinction. Camp is aligned right with the end of Triassic mass extinction, and the Deccan traps are associated with the end Cretaceous mass extinction. So these last three of the big five are certainly related in some way, shape, or form with flood basalt events. There are other flood basalts that have occurred which have not produced mass extinctions. They are related to other lesser extinction level events. There are other possibilities with extinction events for sure. We know about the flood basalts and we have those documented fairly well. But there are other things like methane hydrates, which are frozen methane deposits on the seafloor, and we don't know a whole lot about them. We're just beginning to discover them. And what we think is that if those were melted somehow and that methane changed form and was released into the atmosphere, it could change the climate to some degree. Whether that's related to the eruption of the flood basalts or not, we don't know, but it's a possibility. So an extinction that doesn't really get a whole lot of notoriety, but it was very important because it paves the way for dinosaur rule.